Hi! In this video, I'll be going through how to use the Archimedean property and least upper bound property to prove more theorems. So we really want to practice very hard so that we really understand how to write and use this least upper bound property of the real numbers. So we want to prove more theorems about the real numbers. And so let's first start with an easy one where we just take if a is an element of the real numbers and such that a is always less than epsilon for any given epsilon larger than 0, then a equals to 0. And the proof is simple because let's suppose a does not equal to 0 and we already know that a is greater than 0, so we just say a must be strictly greater than 0. Then we just take epsilon to be half of a, and we see that epsilon naught is less than a now. And this is false because a has to be less than epsilon for every given epsilon, and so a must be 0. And it's easy to extend this to show that if this inequality is further reduced to equality, it can equal to epsilon, it will still hold true and a equals to 0. This formulation is particularly useful because when we deal with limits, we really want to take for every epsilon and show that the limit is equals to something. And so by proving this, it will help us later on when we go into further details in real analysis. And so let's take another example to see how we apply this theorem 2.1.9. So let's take the set of 1 over n's. We want to show that the increment, meaning the greatest lower bound, is 0. So first of all, we know that this is non-empty and is bounded below by 0. And so now we want to prove that 0 is the increment. So we let w be the increment of s, and w must be greater or equal to 0 based on the definition of increment. So we have like one part of here already. So we just need to show that for any epsilon is less than. So we just take for any epsilon greater than 0. The Archimedean property implies that there exists a number n such that 1 over epsilon is less than n. And this implies that 1 over n is less than epsilon and we get our desired property over here. So w must equal to 0 and we're done. So this example is fairly straightforward, and now we'll really be spending the time to think about and understand a bigger and a more important example, which is to show that there exists only one positive real number such that y to the power n equals to x for any real x and any integer n. So how do we prove this? We will go through it slowly because this is something that we really want to understand. And first, let's just read the proof from Rudin. So it is clear that there is at most one y, but why would there exist a y would be what we are trying to answer. So this, because if there exists two y's, one must be greater than the other, and if you raise it to the power n, y2 must still be greater than y1. And so for the equality to, if they are equal, then they must be the same. y1 must equal to y2. And so we just let we define E to be the set of all positive real numbers t such that Tn is less than x. So basically E equals to t as an element of real with the condition that Tn is less than x. So what we really want to show that first, we want to show that E is non-empty and that E is bounded above. So using this x over 1 plus x, we show that it is less than x and t to the power n is less than x. So there exists an element in E already. So E is non-empty. And it's quite easy to see when that this set is bounded Because if t is greater than 1 plus x, when you raise it to the power n, then it will still be greater than x. And so 1 plus x is an upper bound of e. And because of this, it means that the supremum exists. And so now we want to prove that y to the power n equals to x. And this y is the supremum of e. So first, let's say we have this identity where b to the power n minus a actually equals to this following term. And so because b is greater than a, this whole part all the a's here can be replaced by b, and it will just be b to the power n minus 1, n copies. So b to the power n minus a to the power n is less than this term. And so now we assume that y to the power n is less than x. So we choose, let's just read the proof first before I give you an understanding of why we have chosen h to be the following. So from Rudin, he just says that we just choose h to be between 0 and 1 and h to be less than this complicated looking thing. And then we set the a to be y and b to be y plus h. Then we see that y plus h to the power n minus y to the power n be less than this, where we replace accordingly, must be less than the following because h can be replaced. And so it will be actually less than x minus y to the power n. And so we can cancel the y to the power n, and we just show that y plus h to the power n is less than x. But this can't be true because it means that y plus h is an element of e, and because y plus h is greater than y, it contradicts the fact that y is an upper bound of e. So we see that the proof there's no worries, but we really want to think about how we get this choosing of h. So let's imagine that we have this picture over here, now being y less than x to the power 1 over n. What we want is we want to find some guy inside here such that when you take to the power n, it will lie in between y to the power n and x. And so what we really need is we need the h to be satisfying the following. That means the distance between y plus h to the power n to y to the power n is less than the distance from x to y to the power n. And so for this to occur, it's just saying, if we want this to occur, it can be reduced to saying we want h times n times y plus h to the power n minus 1 to be less than epsilon. And in this case, epsilon is x minus y to the power n. And so if h satisfies the first inequality, then it satisfies what we want. Because if you know this is true, then you know this whole thing is true as well. And that's what we want. So we need the h to be less than epsilon over m bracket y plus h to the power n minus 1. But we can't choose this because there is h here and h in the bottom. And so if we introduce another inequality such as h being less than 1, then we can replace the star inequality with epsilon over m bracket y plus 1 power n minus 1. Because now let's say if h is greater than 2, or h equals to 2 basically. If h is bigger than 2, then here if you replace by 2, it will result in something smaller. And so you just need to choose the smaller of the two values. So we can just choose a h between 0 and 1, and then we just change this bottom h to 1, and we just need to choose it to be less than this as well. And this will satisfy our conditions for inequality 1. And with that, it allows us to understand this, how Rudin chooses his h, which results in the contradiction that we want. Hence, y to the power n cannot be less than x. And next, we'll now show why y to the power n cannot be greater than x as well, which is the same argument, but it's easier actually. We choose now the h to be y to the power n minus x over n times y to the power n minus 1. And really, what we want to picture is now that there exists a number between y and x to the power 1 over n, such that when you take the power, it is still within the desired range. And this shows that y to the power n cannot be the supremum, cannot equals to x. So we pick a k such that y to the power n minus y minus k to the power n is less than epsilon. And this epsilon is equals to y to the power n minus x. And so if k satisfies the inequality of k to the power n times y to the power n minus 1, and how we got this is really from the identity here. If we satisfy this, it means that the original inequality we want is satisfied. And so we can see that this part is very simple to do because k is just less than epsilon over n times y to the power n minus 1. And unlike the previous case, in this case now, the y is not in terms of k. And so really we can just choose k to equal to epsilon over n times y to the power n minus 1, and we're done. And so I hope this proof is clear to you, and if it's not, then you can repeat the video and try it out for yourself. This case is a very good example of showing that there exists a positive real root for the equation y to the power n equals to x for any real number x. And so I urge you to understand this example, but I want you to understand that this theorem only holds true for real numbers because you're using the supremum property. And that's all for this video, so I'll catch you in the next one. Bye!